Hey there, and welcome. So, whether you're cramming for an exam or you're just really curious about how radar works, you've come to the right place. Today, we're going to break down radar indicators and antennas. We'll start with what the operator sees on the screen and work our way all the way back to the antenna that's actually scanning the sky. Ready? Let's dive in. So, this is really the big question, isn't it? How do you take invisible radio waves, which are zipping through the air, and turn them into a clear, usable map on a screen? I mean, these systems are processing millions of data points every single second. So how does all that energy become those simple little blips we all recognize? Well, let's start where it all comes together, the display itself. All right, part one. We are starting our journey right where the operator would, staring at the screen. We're going to look at the device that makes it all visible, the radar indicator. This thing is the crucial link between all that raw data coming in from the sky and the human who has to make sense of it all. The best way to think about a radar indicator is as a master translator. Our source material explains that the radar receiver is just getting flooded with information, constantly. The indicator's job is to cut through all that noise and paint a clear, steady picture. It's the part of the system that takes this absolute storm of electronic data and turns it into something a person can actually look at and use. Okay, so not all radar displays are created equal. Different jobs need different kinds of views. So let's meet the three most common types of displays, which are usually just called scopes. First up, we've got the A scope. This is the most basic one. If you look at the diagram, that horizontal line represents distance, or what we call range. See that vertical spike, that blip? That's the echo bouncing off a target. And how tall it is tells you how strong the echo is. The big takeaway here is that the A scope is all about precision. It's perfect when you need the exact distance to one single target, which is why it's so critical for things like weapon control systems. Next up is the RHI, which stands for Range Height Indicator. Now, the easiest way to wrap your head around this one is to imagine turning a radar on its side. The sweep starts at your position, down in the bottom left, and then fans out and up, giving you a side view of the sky. So it doesn't just show how far away something is, but, and this is key, it shows its altitude. This makes it the absolute go-to display for any height-finding radars, which are essential for air traffic control. And finally, we have the one you probably think of when you hear the word radar, the PPI, or Plan Position Indicator. This is that classic top-down 360-degree map. Your radar is right there in the center, and that sweeping line just paints a picture of everything around you, showing both its distance, that's the range, and its direction, which is called the bearing. And there's a good reason it's the most common display. It gives you a complete, totally intuitive picture of what's going on. So we know what a PPI scope shows us. That makes sense, but how does it actually do that? How does it create that smoothly rotating sweep and paint those little targets onto the screen? It's time to pull back the curtain and take a look at the electronics that make the magic happen. Okay, I know this diagram looks a little intimidating, but don't worry. We're only going to focus on one big idea here: synchronization. See, to draw that 360-degree mount correctly, the system has to time three things perfectly: the initial pulse going out, the physical position of the antenna, and the echoes coming back. If that timing is off by even a fraction of a second, the whole map is basically useless. Let's break that big diagram down into four main jobs. First, you've got the gate circuit. Think of it as the master clock, or the conductor of the orchestra, making sure everything happens at the exact right time. Then there's the sweep generator. Its job is to create the voltage that draws that line from the center of the screen out to the edge. The sweep control circuit gets data on where the real antenna is pointing, and it uses that to rotate the line on the screen. And finally, the video amplifier takes that faint little echo signal and juices it up, making it strong enough to light up the screen as a bright blip. So, how does that line on the screen rotate in perfect sync with that big physical antenna? Now, you might be picturing some kind of complex mechanical gears spinning inside the display, right? But modern systems use something way cooler and much more reliable: electromagnetism. Inside the display, they use magnetic fields to steer the beam of electrons. It's kind of like using invisible hands to aim a pen. This electronic method is way faster and more accurate than any clunky mechanical parts could ever be. And this diagram here shows exactly how that works. You've got two sets of magnetic coils. One pushes the beam left and right, and the other pushes it up and down. By perfectly controlling the amount of electricity, the current, going to each set of coils, you can combine their forces to point that electron beam literally anywhere on the screen you want. This is how you make sure the sweep on the display is a perfect mirror of where the real antenna is pointing. Okay, so we can see the targets. That's great. But sometimes just knowing a target is over there isn't good enough. You need to know the exact range. So let's check out the specialized circuits that let operators measure distance with incredible precision. So for those times when you need the exact range to one specific target, you use what's called a range gate generator. You can think of it like a digital magnifying glass, just for distance. This circuit puts a small, movable marker, the gate, on the screen. The operator just slides this gate right over a target's blip, and bam, the system gives them a super precise digital readout of that target's range while totally ignoring everything else on the screen. Now, for a quick sense of scale, operators rely on the range marker generator. This is the circuit that creates those familiar concentric circles you see on a PPI scope. They work just like the distance rings on a map. Each circle represents a set distance, like 5 miles, 10 miles, 15 miles, and so on. This lets the operator estimate the range to any target just by looking, without having to measure each one individually. It's a huge time saver. And if we hop back to our simple A-scope for a second, there's another clever tool called a range step. This circuit creates a little step right on that horizontal line. The operator then uses a dial to slide that step left or right until its front edge lines up perfectly with the very beginning of the target's echo. They can then just read the exact range off a calibrated dial. It's a simple, manual tool, but it's incredibly effective. All right. We have spent a lot of time looking at the screen. Now let's jump to the other end of the system, to the part that actually sends the radio waves out and listens for them to come back. It is time to talk about the eyes of the radar, the antenna. The most important concept to get with antennas is something called directivity. Okay, so on one hand, you have an omnidirectional antenna. This thing is like a bare light bulb. It just throws energy out in all directions at once. That's fine for your car radio, but it's totally useless for radar because you'd have no idea which direction an echo came from. For radar, you need a directional antenna. This acts more like a flashlight or a laser pointer, focusing all of its energy into a tight, narrow beam so you know exactly where you're pointing. So, what's the most common way to create that focused flashlight-like beam? It's with a parabolic reflector. This is that classic dish shape you see everywhere, from satellite TV to huge radar installations. That specific curve isn't random. It's mathematically designed to grab radio energy and concentrate it into one tight, powerful beam. This diagram shows exactly how it works, and honestly, the principle is identical to the reflector in a flashlight. The part that actually creates the radio waves, which is called the feed horn, is placed right at that sweet spot, the focal point, labeled F. Then, the curved dish catches all the energy that radiates from that point and reflects it all forward in perfectly parallel lines. And that's how you create that tight, directional beam you need. So just remember, the dish itself doesn't create any energy. Its only job is to focus it. Okay, we've covered the screens, the circuits that drive them, and the antennas that feed them information. You now have the complete picture, from the sky all the way to the screen. To make sure these ideas really stick, especially if you're studying, let's run through a super quick review and a couple of practice questions. All right, let's do a rapid-fire recap. Ready? A-scope is for range versus strength. RHI scope is range versus height. PPI scope is that 360-degree map. A range gate is for precise single-target ranging. And a parabolic reflector is the dish that focuses the energy beam. Got it? Good. Let's see what you remember. Time for a quick quiz. Question number 1. What are the two main coordinates you see on a PPI scope? Think about that classic map view. I'll give you a second. The answer is range, which is your distance, and bearing, which is your direction. And for our final thought, let's try to apply all this. Now that you know all the building blocks, think about this. How would you combine them to manage a super busy airport? Well, you definitely need a PPI scope for that big picture 360-degree view of all the traffic, right? You probably use RHI scopes to manage the altitudes of planes as they take off and land. And you'd be using precise ranging circuits to make sure there's safe separation between every single aircraft. See, it's all about using the right tool for the right job. Thanks for sticking with me for this deep dive on radar indicators and antennas.